Welcome to this quiet journey through the cosmos, a gentle exploration designed for those peaceful moments when the day has ended and the night stretches out before you, like an endless ocean of possibility. Wherever you are right now, whether you are lying in bed with the covers pulled up softly around you, or sitting in a comfortable chair with the lights dimmed low, or perhaps resting on a couch in that perfect position where your body feels weightless and supported all at once, I invite you to settle in completely. Let your shoulders drop away from your ears. Let your jaw unclench if it has been holding tension. Let your breathing slow down to match the rhythm of calm waves touching a distant shore. Feel the surface beneath you supporting your weight entirely, so that you do not have to hold yourself up anymore, so that you can simply exist without effort in this moment. Tonight we are going to drift together through the vast quietness of space, not rushing or chasing after facts and figures, but floating peacefully through one of the most profound mysteries that exists in all of cosmology. A puzzle that has occupied the minds of scientists for decades, and that reveals something deeply strange about the universe we inhabit. We will explore the question of why the universe is bigger than it should be, why the distances we measure do not match the predictions we make, why the cosmos seems to have expanded more than our best theories suggest it ought to have. But we will take our time getting there, moving slowly like light traveling across billions of years, letting each concept settle into your mind gently before moving on to the next. There is no hurry in the cosmos. The universe has been expanding for nearly 14 billion years, and it will continue expanding for trillions more. And in that vast expanse of time, this moment right now is yours to simply be at peace, to let your thoughts become as soft and diffuse as a nebula, to allow yourself to sink deeper into comfort with every breath you take. So close your eyes, if you have not already, or let them rest half open and unfocused on some dim point in the room. And together, we will begin our slow journey outward from Earth, leaving behind the bright lights and loud sounds of daily life, ascending gently through the atmosphere, rising past the edge of space, where the sky turns black and stars appear in countless numbers. And then continuing outward into the cosmic ocean, where distance is measured in light years and where the expansion of space itself becomes visible. We begin now, drifting peacefully toward an understanding of why our universe is larger than it should be. The view from Earth. As we begin our slow ascent into the cosmos, let us first ground ourselves on Earth, looking up at the night sky just as humans have done for countless thousands of years, trying to understand what we see and what it means. When you look up on a clear, dark night, away from the light pollution of cities, you can see perhaps 2,000 or 3,000 stars with your naked eyes. Tiny points of light scattered across the darkness, some bright and some faint, some clustered into patterns that ancient peoples recognized as constellations. These stars are all part of our galaxy, the Milky Way, a vast island of hundreds of billions of stars bound together by gravity, and every star you see is relatively close to us in cosmic terms, within a few thousand light years at most, near neighbors in the grand scheme of the universe. But there is much more to see than just stars. For scattered among the stars are faint fuzzy patches that do not look like points, but rather like small clouds or smudges. And some of these fuzzy patches are distant galaxies, entire collections of billions of stars so far away that their light has been traveling through space for millions or even billions of years before reaching your eyes. When ancient astronomers looked at these fuzzy patches, they did not know what they were, calling them nebulae, which simply means clouds, thinking perhaps that they were regions of glowing gas within our own galaxy. It was not until the early 20th century that astronomers finally understood that some of these nebulas were in fact distant galaxies, separate islands of stars far beyond the boundaries of the Milky Way. And this realization transformed our understanding of the universe, revealing that the cosmos is vastly larger than anyone had imagined. The person who made this discovery was Edwin Hubble, working at the Mount Wilson Observatory in California in the 1920s, using what was then the most powerful telescope in the world to study these mysterious fuzzy patches in detail. Hubble's revolutionary discovery. Let us drift back in time now, floating gently through the decades to the 1920s, to a time when the nature of the universe was still deeply uncertain and when scientists debated whether the Milky Way was the entirety of the cosmos or merely one galaxy among many. Edwin Hubble was studying a particular fuzzy patch called the Andromeda Nebula, taking photographs of it night after night, measuring the brightness of individual stars he could barely resolve within it. Among these stars, he found several that belonged to a special class called Cepheid variables, stars that pulse in and out, growing brighter and dimmer in a regular cycle. And these stars were valuable because their pulsation period is directly related to their intrinsic brightness, meaning that by measuring how fast they pulse, you can determine how bright they actually are, and by comparing that to how bright they appear, you can calculate how far away they must be. When Hubble did these calculations for the Cepheid variables in Andromeda, he found that they were incredibly distant, much too far away to be within the Milky Way, proving that Andromeda was a separate galaxy in its own right, a collection of hundreds of billions of stars lying about 2 million light-years away from us. This discovery was revolutionary, for it meant that the universe was far larger than anyone had thought, filled not just with one galaxy, but with countless galaxies spread throughout space, each one an island of stars separated from its neighbors by vast gulfs of emptiness. But Hubble did not stop there, for he continued measuring distances to other galaxies, building up a catalog of how far away various galaxies were. And as he did so, he noticed something even more remarkable, something that would change our understanding of the universe in ways that are still echoing through cosmology today. The discovery of cosmic expansion. As Hubble measured the distances to more and more galaxies, he also measured something else about them, their velocities, how fast they were moving relative to Earth. This measurement came from studying the spectra of galaxies, the patterns of light they emit at different wavelengths. For the spectra contain dark lines at specific wavelengths where certain elements absorb light. And by comparing where these lines appear in a galaxy's spectrum to where they appear in a laboratory, Hubble could determine whether the galaxy was moving toward us or away from us. If a galaxy is moving away, its light is stretched to longer wavelengths, shifted toward the red end of the spectrum in what is called redshift. And if it is moving toward us, its light is compressed to shorter wavelengths, shifted toward the blue in what is called blue shift. Most galaxies that Hubble observed were redshifted, meaning they were moving away from us, and the farther away a galaxy was, the faster it seemed to be receding. This relationship between distance and velocity became known as Hubble's law, and it suggested something profound about the nature of space itself. Something that went far beyond the simple motion of galaxies through a static background. The galaxies were not simply moving through space, flying away from us like debris from an explosion, but rather space itself was expanding, carrying the galaxies along with it like raisins in a rising loaf of bread. This expansion means that the universe itself is growing larger over time, that the distances between galaxies are increasing, not because the galaxies are moving, but because the space between them is stretching. And this revelation transformed cosmology. providing the first concrete evidence that the universe has a history, that it has not always been the same size, but has been expanding from a denser, hotter state in the past. The implications of expansion. Let us pause here and drift quietly through this concept, letting it settle into your awareness, for the expansion of the universe is one of those ideas that seems simple on the surface, but that has profound and sometimes counterintuitive implications. If space is expanding, carrying galaxies away from each other, then we can imagine running the cosmic movie backward, imagining what would happen if we reverse the expansion, if we watch the universe contracting instead of growing. As we run time backward, galaxies get closer together. The universe becomes denser and hotter. And eventually, we reach a point where all the matter and energy in the universe was compressed into a tiny volume, a state of unimaginable density and temperature that we call the Big Bang. This is not an explosion in space, but rather an expansion of space itself. The beginning of space and time and matter and energy all at once. And from this beginning, the universe has been expanding and cooling for nearly 14 billion years, evolving from a hot, dense plasma into the vast cosmos we see today, filled with stars and galaxies and the cold darkness of intergalactic space. The expansion also means that the universe has no center and no edge in the usual sense, for every point in space is expanding away from every other point. And from the perspective of any observer in any galaxy, it would appear that all the other galaxies are moving away, just as we see them moving away from us. This is sometimes illustrated with the raisin bread analogy, imagining the universe as bread dough rising in an oven, with galaxies as raisins embedded in the dough, and as the dough expands, every raisin sees every other raisin moving away, with no raisin being at the center of the expansion. The expansion of space also affects light traveling through it. For as space expands, the wavelength of light is stretched along with it, causing the light from distant galaxies to be redshifted not just because of their motion, but because of the expansion of space itself. Measuring the universe. As we continue our drift through the cosmos, floating gently past galaxies and clusters of galaxies, let us consider how astronomers measure the vast distances that separate these objects. For understanding the size of the universe requires measuring distances to objects that are incredibly far away, so far that light from them has been traveling through space for billions of years. The method Hubble used, observing Cepheid variable stars, works well for relatively nearby galaxies, those within a few tens of millions of light years. But beyond that distance, individual stars become too faint to see even with powerful telescopes, and astronomers must use other methods. One of the most important tools for measuring cosmic distances is the Type Ia supernova, a particular kind of stellar explosion that occurs when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion star until it reaches a critical mass, about 1.4 times the mass of the Sun, at which point it explodes catastrophically, releasing in a few weeks as much energy as the Sun will produce over its entire 10 billion year lifetime. Type Ia supernovae are valuable as distance indicators because they all have roughly the same intrinsic brightness at their peak, shining with the light of billions of suns. And because they are so bright, they can be seen across vast distances, billions of light years away, allowing astronomers to measure distances to galaxies that are too far for other methods. By observing supernovae in distant galaxies, measuring their apparent brightness and comparing it to their known intrinsic brightness, astronomers can calculate how far away the host galaxies are. And by also measuring the redshift of those galaxies, They can determine the relationship between distance and redshift, which tells us about the expansion rate of the universe. The Hubble constant and cosmic expansion rate. The relationship between distance and velocity in the expanding universe is characterized by a number called the Hubble constant, named after Edwin Hubble, who first discovered the expansion. And this constant tells us how fast the universe is expanding, how rapidly galaxies are receding from each other due to the expansion of space. The Hubble constant is typically expressed in units of kilometers per second per megaparsec, which means that for every megaparsec of distance, about 3.26 million light years, the recession velocity increases by a certain number of kilometers per second. The exact value of the Hubble constant has been one of the most important questions in cosmology for decades, for it tells us not just about the current expansion rate, but also about the age of the universe and its ultimate fate, whether it will expand forever or eventually recollapse. Measuring the Hubble constant precisely is challenging because it requires measuring both distances and velocities accurately across a wide range of scales. From nearby galaxies where distances can be measured with Cepheid variables to distant galaxies where supernovae must be used. And different methods sometimes give slightly different results, leading to what astronomers call the Hubble tension, a persistent discrepancy between measurements made using different techniques. Some methods, particularly those that observe the cosmic microwave background radiation, the faint glow left over from the Big Bang, suggest a Hubble constant of about 67 kilometers per second per megaparsec, while other methods, based on observations of supernovae and Cepheid variables in nearby and distant galaxies, suggest a value of about 73, a difference of about 10% that may seem small, but that is statistically significant and that suggests something interesting is happening that we do not fully understand. The paradox emerges. Let us drift now toward the heart of our mystery, toward the question of why the universe is bigger than it should be. For this puzzle emerges from careful measurements of cosmic distances and from comparisons between what we observe and what our theories predict. When astronomers measure distances to very distant galaxies, galaxies whose light has been traveling toward us for billions of years, they find that these galaxies are farther away than simple calculations based on the expansion rate would suggest. If the universe has been expanding at a constant rate since the Big Bang, then we can calculate how far light should have traveled in a given amount of time. And from that, we can predict how far away a galaxy with a particular redshift should be. But when these predictions are compared to actual measurements, the galaxies turn out to be more distant than expected, as if the universe has somehow grown larger than it ought to have, as if the expansion has proceeded faster or for longer than our simple models suggest. This discrepancy is subtle, not a dramatic difference, but a systematic trend that shows up when many measurements are combined. And it has led cosmologists to propose that the expansion of the universe is not constant, but is accelerating. That the rate at which space expands is actually increasing over time, rather than staying the same or slowing down as gravity might be expected to cause. This acceleration was discovered in the late 1990s by two independent teams of astronomers studying distant Type Ia supernovae, and it was so unexpected that it was initially greeted with skepticism, for it implied the existence of something completely new, an unknown form of energy that fills all of space and that drives the accelerated expansion. Dark energy and the accelerating universe. The mysterious force that causes the universe's expansion to accelerate has been given the name dark energy, a placeholder term that reflects our profound ignorance about what it actually is. For dark energy does not emit light, does not clump together like matter. and does not interact with ordinary matter or radiation in any way that we can directly detect except through its gravitational effects on the expansion of space. Dark energy appears to be a property of space itself, a form of energy that remains constant in density even as space expands, so that as the universe grows larger, the total amount of dark energy increases. And this energy acts like a repulsive force, pushing space to expand faster and faster over time. The existence of dark energy solves the paradox of why the universe is bigger than it should be. For if the expansion has been accelerating for the past several billion years, then distant galaxies have had more time to move away from us than they would have if the expansion had been constant or decelerating. And this extra expansion explains why we see them farther away than simple models predict. Dark energy is now thought to make up about 68% of the total energy content of the universe, far more than ordinary matter, which makes up only about 5%, or dark matter, which makes up about 27%, making dark energy the dominant component of the cosmos, even though we have no idea what it is or why it exists. The discovery of dark energy and cosmic acceleration earned the Nobel Prize in Physics in 2011, recognizing the profound implications of this finding for our understanding of the universe and its fate. The geometry of space. As we drift through the expanding cosmos, let us consider another aspect of this mystery: the geometry of space itself, for the shape of the universe, on the largest scales, affects how light travels through it and how distances are related to observed redshifts. In Einstein's theory of general relativity, which is our best description of how gravity works, space is not a rigid background, but a flexible entity that can be curved by the presence of matter and energy. And the overall geometry of the universe depends on the total amount of matter and energy it contains. If the universe contains exactly the critical amount of matter and energy, then space is flat, meaning that parallel lines remain parallel forever, and that the angles of a triangle add up to exactly 180 degrees, just as they do in the geometry we learn in school. If the universe contains more than the critical amount, then space is positively curved, like the surface of a sphere, and parallel lines eventually converge, and triangles have angles that add up to more than 180 degrees. If the universe contains less than the critical amount, then space is negatively curved, like a saddle, and parallel lines diverge, and triangles have angles that add up to less than 180 degrees. Measurements of the cosmic microwave background radiation, which provides a snapshot of the universe when it was only about 380,000 years old, show that space is flat to within a small margin of error, meaning that the total energy density of the universe is very close to the critical density. This flatness requires a precise balance between different components: ordinary matter and dark energy, all combining to give exactly the right total. And the fact that this balance exists is itself somewhat mysterious, for there is no obvious reason why the universe should be so close to flat, rather than strongly curved one way or the other. Looking back through time, one of the most remarkable aspects of astronomy is that when we look at distant objects, we are also looking back in time. For light travels at a finite speed, about 300,000 kilometers per second, and light from distant sources takes time to reach us, sometimes billions of years. This means that when we observe a galaxy that is 10 billion light years away, we are seeing that galaxy as it was 10 billion years ago, when the universe was less than a quarter of its current age, and the light we receive has been traveling through expanding space all that time, being stretched by the expansion and redshifted to longer wavelengths. The farther away we look, the farther back in time we see. And the more dramatic the effects of cosmic expansion become, For the universe was smaller and denser in the past, and the expansion rate was different, generally faster in the early universe when gravity was trying to slow the expansion down against the kinetic energy of the Big Bang. By observing galaxies at different distances, astronomers are effectively sampling different epochs of cosmic history, seeing how galaxies and the universe itself have evolved over time. And these observations provide crucial tests of cosmological models, allowing us to determine whether our understanding of cosmic expansion and dark energy is correct. The deepest images taken by powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope reveal galaxies that formed when the universe was only a few 100 million years old. Galaxies whose light has been traveling toward us for over 13 billion years. And studying these ancient galaxies helps us understand how the first stars and galaxies formed and how the universe evolved from the smooth, hot state of the early Big Bang to the lumpy, structured cosmos we see today. The cosmic microwave background. Let us drift now to one of the most important sources of information about the early universe. A faint glow of radiation that fills all of space and that comes from every direction with almost perfect uniformity. The cosmic microwave background radiation, often abbreviated as CMB. This radiation is the afterglow of the Big Bang, the cooled remnant of the intense heat that filled the early universe. And it provides a snapshot of what the cosmos looked like when it was only about 380,000 years old, long before any stars or galaxies had formed. At that early time, the universe was filled with a hot, dense plasma of electrons and protons and photons, all colliding with each other constantly, and the photons could not travel far without scattering off electrons, making the universe opaque like a thick fog. But as the universe expanded and cooled, the temperature eventually dropped below about 3,000 degrees, cool enough that electrons and protons could combine to form neutral hydrogen atoms. And when this happened, the photons were suddenly free to travel unimpeded across space. For neutral hydrogen does not interact strongly with light. The universe became transparent, and the photons that were released at that moment have been traveling freely ever since. Their wavelengths stretched by the expansion of space from visible and infrared light into microwaves, which is why we now detect them as the cosmic microwave background. The CMB was predicted by theory in the 1940s, but not discovered until 1965. When two radio astronomers, Arno Penzias and Robert Wilson, detected a persistent noise in their antenna that came from all directions and that they eventually realized was the cosmic microwave background, earning them the Nobel Prize in Physics. The sound of the early universe. When we study the cosmic microwave background in detail, mapping its temperature in different directions of the sky with great precision, we find that it is not perfectly uniform, but shows tiny variations. Hot and cold spots that differ in temperature by only about 1 part in 100,000. These variations are incredibly important because they represent density fluctuations in the early universe, regions that were slightly denser or slightly less dense than average. And these density fluctuations were the seeds from which all structure in the universe eventually grew. The denser regions had slightly stronger gravity, which attracted more matter, making them even denser. And over billions of years, these small initial fluctuations were amplified by gravity until they became the galaxies and galaxy clusters we see today. The pattern of hot and cold spots in the CMB contains a wealth of information about the early universe, encoded in the sizes and amplitudes of the fluctuations. And by analyzing this pattern, cosmologists can determine fundamental properties of the universe, like its age, its composition, its geometry, and its expansion history. The pattern can be thought of as a fossil record of sound waves that were traveling through the plasma of the early universe. Pressure waves created by the interplay between gravity, trying to compress the plasma, and radiation pressure trying to push it apart. And these sound waves created oscillations in density that show up as peaks and troughs in the statistical analysis of the CMB temperature variations. By measuring the positions and heights of these peaks, cosmologists have been able to determine that the universe is about 13.8 billion years old, that it is spatially flat, that it contains about 5% ordinary matter, 27% dark matter, and 68% dark energy, and that the current expansion rate is about 67 kilometers per second per megaparsec, all with remarkable precision. The horizon problem. As we drift through our exploration of cosmic mysteries, let us consider one of the puzzles that has occupied cosmologists for decades. A puzzle related to the uniformity of the cosmic microwave background, and to the question of why different parts of the universe seem to have the same properties, even though they should never have been in contact with each other. The CMB is remarkably uniform, with the same temperature in all directions to better than 1 part in 100,000. And this uniformity tells us that the entire observable universe was at the same temperature when the CMB was formed, suggesting that all regions had reached thermal equilibrium, meaning they had time to exchange energy and come to the same temperature. But here's the puzzle. If we calculate how far light could have traveled in the 380,000 years between the Big Bang and the formation of the CMB, we find that it is much smaller than the size of the observable universe at that time, meaning that distant regions of the CMB should not have been able to communicate with each other, should not have been able to exchange energy and reach the same temperature, and yet they clearly have the same temperature. This is called the horizon problem, for it asks why regions that are beyond each other's horizons, beyond the distance that light could have traveled to connect them, nevertheless have identical properties. The standard Big Bang model does not provide a satisfactory answer to this problem, for in that model the universe simply starts out uniform, without explanation. But there is a modification to the Big Bang model that solves the horizon problem elegantly, a brief period of exponentially fast expansion in the very early universe called cosmic inflation. The theory of cosmic inflation let us float gently into one of the most important ideas in modern cosmology, the theory of cosmic inflation, which proposes that the universe underwent a brief period of extraordinarily rapid expansion in the first tiny fraction of a second after the Big Bang, expanding by a factor of at least 10 to the 26 in a time interval of perhaps 10 to the minus 32 seconds, causing a region of space that was originally smaller than an atom to grow to the size of a grapefruit or larger, and in the process smoothing out any initial irregularities and setting the stage for the more sedate expansion that has continued ever since. Inflation solves the horizon problem because during the inflationary period, all the parts of the currently observable universe were once close enough together to be in thermal contact, allowing them to reach the same temperature. And then inflation stretched them apart so rapidly that they are now separated by vast distances, but still have the same properties. Inflation also solves another problem called the flatness problem, which asks why the geometry of the universe is so close to flat, when even small deviations from flatness in the early universe would have been amplified over time to make the universe strongly curved today. Inflation solves this because the rapid expansion during inflation stretches space so much that any initial curvature becomes negligible, like the way the surface of a balloon appears flatter and flatter as the balloon is inflated to larger and larger sizes. The theory of inflation was proposed by Alan Guth and others in the early 1980s, and it has become a central part of modern cosmology, explaining not just the horizon and flatness problems, but also providing a mechanism for generating the tiny density fluctuations that we see in the cosmic microwave background. For quantum fluctuations during inflation are stretched to cosmic sizes and become the seeds of structure formation. Quantum fluctuations and structure formation. As we drift through the concept of inflation, let us pause and consider one of its most profound implications: the idea that the structure we see in the universe today, all the galaxies and galaxy clusters, and the vast cosmic web of filaments and voids, ultimately originated from quantum fluctuations, tiny random variations in energy density that occurred at the quantum level during the inflationary period. Quantum mechanics tells us that even in empty space, there are always fluctuations, brief moments when energy appears and disappears due to the uncertainty principle, creating virtual particles that pop into existence and then annihilate each other almost immediately. During inflation, these quantum fluctuations were stretched by the rapid expansion of space, amplified from subatomic scales to cosmic scales, and frozen into the fabric of space as permanent variations in density. When inflation ended and the universe transitioned to the slower expansion of the standard Big Bang, these density variations became the seeds for structure formation. For the slightly denser regions attracted more matter through gravity and grew over time, eventually collapsing to form the first stars and galaxies, while the less dense regions remained relatively empty, becoming the voids we see in the cosmic web. This connection between quantum mechanics and cosmology is one of the most beautiful and surprising insights in modern physics, for it suggests that the grand structure of the universe, the distribution of galaxies across billions of light years, ultimately has its origin in the strange probabilistic world of quantum fluctuations. In events that occurred when the universe was so small and so young that the distinction between quantum mechanics and cosmology breaks down. The predictions of inflation for the pattern of fluctuations in the CMB have been tested with remarkable precision by satellite missions like WMAP and Planck, and the observations match the theoretical predictions extraordinarily well, providing strong support for the inflationary paradigm. The multiverse possibility. Let us drift now into more speculative territory, considering one of the implications of inflation that has captured the imagination of physicists and the public alike: the possibility that our universe is not unique, but is just one of countless universes in a vast multiverse. A collection of separate space-time regions, each with its own properties and perhaps its own laws of physics. This idea emerges naturally from certain versions of inflation theory, for if inflation is driven by a field called the inflaton field that has potential energy, then in some regions of space the inflaton field might decay and end inflation, creating a bubble universe like ours. While in other regions, inflation might continue, with new bubble universes forming continuously, each one expanding and evolving independently of the others. In this scenario, called eternal inflation, the multiverse as a whole continues inflating forever, spawning new universes endlessly. And each universe might have different values for fundamental constants or even different physical laws depending on how the inflaton field decayed in that region. This possibility is both fascinating and troubling. Fascinating because it suggests that reality is far larger and more diverse than we ever imagined, and troubling because if different universes have different properties, then many of the questions we ask about why our universe has the particular properties it does might not have fundamental answers, but might simply be matters of chance. With our universe being the way it is, because if it were different, we would not be here to observe it, an application of the anthropic principle. The multiverse idea is controversial among physicists because it is difficult or impossible to test, for we cannot observe other universes if they are separate regions of space-time disconnected from our own. And without observational evidence, the multiverse remains a speculation rather than a confirmed theory. Dark matter's role in expansion. Let us return now from speculation to observation, drifting back to the components of the universe that we know exist even if we do not fully understand them, and consider dark matter, the mysterious invisible substance that makes up about 27% of the universe's total energy content. Dark matter does not emit light or any other electromagnetic radiation, making it invisible to telescopes. But we know it exists because of its gravitational effects on visible matter, on the motions of stars within galaxies, on the motions of galaxies within clusters, and on the bending of light from distant sources as it passes near massive objects in a phenomenon called gravitational lensing. Dark matter forms the scaffolding on which galaxies are built, providing the gravitational glue that holds them together and that draws ordinary matter into dense clumps where stars can form. And without dark matter, galaxies as we know them could not exist. For the ordinary matter alone does not have enough gravity to hold itself together against the dispersing effects of rotation and random motion. Dark matter also affects the expansion of the universe, for its gravity tries to slow the expansion down, pulling matter back together, and the amount of dark matter determines how strong this braking effect is. In a universe with more dark matter, the expansion would slow down more quickly, and in a universe with less dark matter, it would slow down more gradually. The presence of dark matter was essential in the early universe for the formation of the first structures, for the dark matter began clumping under its own gravity before ordinary matter did, creating potential wells into which ordinary matter could fall, speeding up the process of galaxy formation. Observations of the cosmic microwave background and of the large-scale structure of the universe allow cosmologists to measure the amount of dark matter with good precision, and these measurements consistently point to dark matter making up about 27% of the total. But the nature of dark matter remains one of the biggest mysteries in physics. The nature of dark matter. As we float through the darkness of space, it is fitting to consider the darkness within the universe itself, the dark matter that surrounds us and permeates every galaxy, but that we cannot see or touch directly. The leading theory is that dark matter consists of particles that were produced in the early universe and that interact only through gravity, and possibly through the weak nuclear force, making them extremely difficult to detect. These particles are collectively called WIMPs, for weakly interacting massive particles, and they would be much heavier than protons or neutrons, perhaps tens or hundreds of times heavier. But they would be so weakly interacting that they could pass through ordinary matter without leaving a trace. Billions of them streaming through your body every second, without you ever noticing. Despite decades of searching with ever more sensitive detectors, physicists have not yet directly detected dark matter particles, and this failure has led some to consider alternative ideas, such as that dark matter might be made of much lighter particles called axions, or that it might not be particles at all, but rather a modification to the laws of gravity that causes gravitational effects to be stronger than Einstein's theory predicts on large scales. Another possibility is that dark matter consists of primordial black holes. Black holes formed in the very early universe from density fluctuations rather than from the collapse of stars. Though observations of gravitational lensing and other phenomena have constrained how many primordial black holes can exist and suggest they cannot account for all the dark matter. The mystery of dark matter is one of the most pressing questions in physics today, for solving it would not only explain a major component of the universe, but might also reveal new physics beyond the standard model of particle physics, potentially opening doors to understanding other mysteries, like the nature of dark energy or the unification of forces. The cosmological constant. Let us drift now toward another mystery, perhaps the deepest one of all. The question of what dark energy actually is and why it has the particular value that it does. The simplest explanation for dark energy is that it is the cosmological constant, a term that Einstein introduced into his equations of general relativity in 1917, but that he later called his greatest blunder. Einstein was trying to construct a model of a static universe, one that neither expands nor contracts. And he found that his original equations did not allow for such a universe because gravity would cause matter to clump together and collapse. To prevent this collapse, he added a new term to his equations, a constant that represented a repulsive force inherent in space itself, balancing gravity and allowing a static universe to exist. When Hubble discovered that the universe is actually expanding, Einstein realized that his cosmological constant was unnecessary for achieving a static universe, though the expansion itself could be explained by the original equations without the constant. But the cosmological constant never quite went away, for theorists realized that there was no fundamental reason why it should be exactly zero, and that a small positive value would act as a repulsive force that could cause the expansion of the universe to accelerate. Exactly what observations of distant supernova later revealed. In modern cosmology, the cosmological constant is interpreted as the energy density of empty space itself, what physicists call vacuum energy, arising from the quantum fluctuations that constantly occur even in the absence of matter and radiation. Quantum field theory predicts that empty space should have energy, but the predicted value is vastly larger than the observed value, larger by a factor of about 10 to the 120. An enormous discrepancy that represents one of the worst failed predictions in the history of physics. And that suggests we are missing something fundamental in our understanding of quantum mechanics or gravity or both. The vacuum energy problem. As we float through the void, through the emptiness between galaxies where matter is sparse and space is nearly empty, let us consider the strange fact that this emptiness is not truly empty, but is filled with energy. The vacuum energy that drives the accelerated expansion of the universe. According to quantum field theory, the vacuum is a seething foam of virtual particles, electron-positron pairs and quark-antiquark pairs and photons that pop into existence from nothing, exist for an infinitesimally brief moment allowed by the uncertainty principle, and then annihilate back into nothing. These virtual particles carry energy, and when you add up the energy contributions from all possible virtual particles at all possible wavelengths, you get an infinite result, which is clearly nonsense. Physicists deal with this infinity by introducing a cutoff, saying that virtual particles with wavelengths shorter than some minimum scale do not contribute. And the choice of where to put this cutoff determines how much vacuum energy you calculate. If you put the cutoff at the Planck scale, the shortest distance that has any meaning in quantum mechanics, about 10 to the minus 35 meters, then the calculated vacuum energy is enormous, about 10 to the 120 times larger than the observed dark energy density. This enormous discrepancy is called the cosmological constant problem, or the vacuum energy problem. And it has resisted solution for decades, despite the best efforts of some of the smartest theoretical physicists in the world. The fact that the vacuum energy is not zero, as one might naively expect, but is instead a tiny positive value, small enough that its effects only became important relatively recently in cosmic history after billions of years of expansion, seems like an incredible coincidence. And it has led some physicists to invoke the anthropic principle, arguing that in a multiverse where different regions have different values of the vacuum energy, we necessarily find ourselves in a region where it is small enough to allow galaxies and stars and planets and life to form. For in regions where it is much larger, the expansion would be so rapid that structure could never form. Measuring cosmic distances with precision. Let us drift back now to the observational side of cosmology, to the careful, painstaking work that astronomers do to measure distances across the cosmos with ever greater precision. For it is these measurements that reveal the paradox of a universe that is bigger than it should be. Measuring cosmic distances is challenging because space is vast and light from distant objects is faint, requiring powerful telescopes and sensitive detectors and careful analysis to extract reliable information. The cosmic distance ladder is the name given to the series of methods that astronomers use to measure distances at different scales. Each method building on the previous one and extending the reach of our measurements farther into space. At the bottom of the ladder are geometric methods like parallax, which uses the apparent shift in position of nearby stars as Earth orbits the Sun to calculate their distances directly. And these parallax measurements provide the foundation for all other distance measurements by establishing the distances to nearby stars with high precision. The next rung of the ladder uses standard candles, objects whose intrinsic brightness is known, and by comparing intrinsic brightness to observed brightness, distances can be calculated. Cepheid variable stars are important standard candles because their pulsation period is tightly correlated with their intrinsic brightness, making them useful for measuring distances to nearby galaxies. Type Ia supernovae are even brighter and can be seen much farther away, extending the distance ladder to billions of light years. And by combining measurements of many supernovae at different distances, astronomers can map out the expansion history of the universe and test cosmological models. More recently, gravitational wave observations have provided a new way to measure cosmic distances. For when two black holes or neutron stars merge, they emit gravitational waves whose amplitude depends on distance. And if the merger produces electromagnetic radiation as well, allowing us to identify the host galaxy, then we can measure both distance and redshift independently, providing a powerful new rung on the distance ladder. The Hubble tension revisited. As measurements of the Hubble constant have become more precise over the past 2 decades, a puzzling discrepancy has emerged that cosmologists call the Hubble tension. And this tension is directly related to the question of why the universe seems bigger than it should be. On one side of the tension are measurements made using the cosmic microwave background, which observe the universe as it was in its infancy and use our best cosmological model to extrapolate forward to the present and predict what the current expansion rate should be. These measurements give a Hubble constant of about 67 kilometers per second per megaparsec, with an uncertainty of only about 1%. On the other side are measurements made using the distance ladder, observing Cepheid variables and Type Ia supernovae in galaxies at various distances and directly measuring the relationship between distance and redshift. These measurements give a Hubble constant of about 73, also with about 1% uncertainty. The difference between 67 and 73 may not sound like much, but it is statistically significant, meaning that it is unlikely to be due to random chance or measurement error, and it suggests that something interesting is happening that our standard cosmological model does not account for. If the local measurements are correct, and the Hubble constant really is about 73, then the universe is expanding faster than the CMB measurements predict, which means that it has grown larger in the time since the CMB was formed than we would expect, making it literally bigger than it should be according to our models. Alternatively, if the CMB measurements are correct, then there must be some systematic error in the local measurements that is causing them to overestimate the expansion rate. But despite intensive efforts to find such errors, none have been convincingly identified. Possible explanations for the tension. Let us drift through some of the possible explanations that have been proposed to resolve the Hubble tension. For this puzzle has prompted cosmologists to reconsider many of their assumptions about how the universe works. One possibility is that there is some new physics involved, something that affects the expansion rate in a way that our current models do not include. For example, dark energy might not be constant, but might evolve over time, becoming stronger or weaker as the universe ages. Or there might be additional forms of energy or matter that we have not yet detected that affect the expansion in subtle ways. Another possibility is that the universe is not as uniform as we think, that we happen to live in a region that is less dense than average. And this local underdensity could cause the expansion rate to appear faster in our neighborhood than it is on average across the whole universe. Yet another possibility is that our understanding of type Ia supernovae as standard candles is not quite right. That there are subtle variations in their intrinsic brightness that correlate with distance or environment in ways that we have not accounted for, causing systematic errors in the distance measurements. Or perhaps the problem lies with the cosmic microwave background analysis, with some aspect of how we model the early universe or extract the Hubble constant from the CMB data. Each of these possibilities has been explored in detail by different research groups, and each faces challenges in explaining the observations without contradicting other well-established results. The Hubble tension remains unresolved as of now, and it is one of the most active areas of research in cosmology, with new observations and new theoretical ideas being proposed regularly as scientists work to understand whether this tension points to a fundamental gap in our understanding of the cosmos, the fate of the universe. As we drift through the expanding cosmos, it is natural to wonder where all this expansion is leading, what the ultimate fate of the universe will be, whether it will expand forever or eventually stop and recollapse, whether stars and galaxies will continue to shine indefinitely, or whether they will eventually fade into darkness. The answer depends on the contents of the universe and on the nature of dark energy. In a universe dominated by matter with no dark energy, the expansion would gradually slow down due to gravity. And depending on the total amount of matter, the universe might eventually stop expanding and begin to recollapse in a big crunch, the time reverse of the Big Bang. Or it might continue expanding forever, but at an ever-decreasing rate. But our universe is not dominated by matter, but by dark energy. And if dark energy is truly a cosmological constant in density as space expands, then the expansion will accelerate forever, with galaxies moving away from each other faster and faster, eventually reaching speeds faster than light, not because they are moving through space, but because space itself is expanding between them. In this scenario, the universe will become an increasingly lonely place. For as expansion accelerates, distant galaxies will eventually recede beyond our cosmic horizon, the distance beyond which their light can never reach us. And they will effectively disappear from our observable universe, winking out one by one as they are carried away by expansion. In the far future, billions of years from now, observers in the Milky Way or in whatever galaxy our Milky Way has merged with will see a much emptier universe than we see today, with only the nearest galaxies still visible, all the rest having been carried beyond the horizon by the accelerating expansion. Deep time and cosmic evolution let us drift forward through time now, imagining the universe as it will be in the distant future. billions and trillions of years from now. When the accelerating expansion has carried most galaxies beyond the horizon, and when the stars that light up the current universe have burned out and faded, the universe of the far future will be a cold, dark place, very different from the vibrant cosmos we see today. In about 1 trillion years, star formation will have ended throughout the universe. For all the gas that can form stars will have been used up, and the last stars will have either exploded as supernova if they were massive, or faded to white dwarfs, and then black dwarfs if they were smaller. Galaxies will have long since merged with their neighbors, creating enormous elliptical galaxies containing the stellar remnants of countless galaxies. And these remnant galaxies will drift alone through space, separated from all other galaxies by distances so vast that no signal from one can ever reach another. Within these galaxies, stellar remnants will slowly evaporate, individual stars being flung out into intergalactic space by gravitational interactions, and over unimaginably long timescales. The galaxies themselves will dissolve. Even black holes, which might seem eternal, will eventually evaporate through a quantum process called Hawking radiation, taking 10 to the 100 years or more to completely disappear. After all the black holes have evaporated, the universe will consist of a dilute gas of elementary particles and photons, all at nearly the same temperature just above absolute zero, expanding forever, growing ever colder and ever emptier, a state called the heat death or the big freeze. And in this final state, nothing interesting will ever happen again, for there will be no energy differences to drive any processes, no stars to shine, no life to evolve, just an eternal, unchanging emptiness. The observable universe and beyond. Let us drift back to the present and consider the relationship between the observable universe and the universe as a whole, for these are not the same thing. And understanding the difference helps us appreciate why the universe might be bigger than we can ever know. The observable universe is the region of space from which light has had time to reach us since the Big Bang. A sphere centered on Earth with a radius of about 46 billion light-years in all directions. This radius is larger than the age of the universe in light-years, which is about 13.8 billion. Because space has been expanding while the light traveled, so the objects that emitted the light we now see are now much farther away than they were when the light was emitted. The boundary of the observable universe is not a physical barrier, but simply a limit to what we can see. And beyond this boundary, there is presumably more universe, more galaxies and stars and planets. But their light has not had time to reach us yet, and if the expansion continues to accelerate, it never will. The universe beyond our observable horizon might be very similar to what we see within it, or it might be different in ways we cannot predict. And we have no way to know for certain because we cannot observe it. Some cosmological models suggest that the universe is infinite in extent, stretching on forever in all directions, in which case there are infinitely many galaxies and infinitely many stars, and given the finite number of ways that matter can be arranged, there would be infinitely many copies of Earth and infinitely many versions of you, living out slightly different lives. This is a strange and unsettling thought, but it follows logically from the assumption of an infinite universe, combined with the observed uniformity of the cosmos on large scales. The role of gravity in cosmic structure. As we float through the cosmos, let us consider the force that shapes everything we see, that pulls matter together into planets and stars and galaxies, and that fights against the expansion of space, trying to pull the universe back together even as dark energy pushes it apart. Gravity is the weakest of the 4 fundamental forces of nature on small scales, far weaker than electromagnetism or the nuclear forces, But it is the only force that matters on cosmic scales because it is always attractive, always pulling matter together, and because it has infinite range, acting across any distance, no matter how large. The story of structure in the universe is the story of the competition between gravity and expansion, between the tendency of matter to clump together and the tendency of space to carry matter apart. In the early universe, shortly after the Big Bang, matter was spread almost uniformly through space, with only tiny variations in density. The fluctuations we see in the cosmic microwave background. But these tiny variations were enough for gravity to begin working. For regions that were slightly denser than average had slightly stronger gravity, attracting more matter from their surroundings and becoming even denser. This process of gravitational amplification proceeded slowly at first, but accelerated over time as the density contrasts grew larger. And eventually, the overdense regions became so dense that they collapsed under their own gravity, forming the first stars and galaxies. The distribution of dark matter played a crucial role in this process because dark matter began clumping earlier than ordinary matter, creating potential wells into which ordinary matter could fall. And the patterns of dark matter clustering determined where galaxies would form and how they would be distributed through space. The cosmic web. When we map the distribution of galaxies across large regions of space, we see that they are not scattered randomly, but are organized into a structure called the cosmic web, a vast network of filaments and sheets surrounding enormous empty voids. The filaments are like threads of a spider web, long, thin concentrations of galaxies stretching across hundreds of millions of light years. And where filaments intersect, we find clusters of galaxies, regions where hundreds or thousands of galaxies are gravitationally bound together in a relatively small volume. The sheets are like walls, two-dimensional surfaces of galaxies that can stretch across even larger distances, and the voids are vast regions containing very few galaxies. Enormous bubbles of nearly empty space that can be 300 million light-years across or more. This cosmic web structure is a direct consequence of how gravity amplifies density fluctuations. For the initial random fluctuations present in the early universe had structure on all scales. And as gravity amplified these fluctuations, matter flowed along the paths of least resistance, creating filaments and sheets rather than uniform spherical concentrations. The cosmic web is visible not just in the distribution of galaxies, but also in the distribution of intergalactic gas, which is heated as it falls into the potential wells of the dark matter filaments, and which emits faint X-rays that can be detected by space telescopes. The web structure is also predicted by computer simulations of structure formation, which start with the initial conditions measured from the cosmic microwave background and evolve them forward through billions of years of gravitational dynamics. And these simulations produce cosmic web structures that look remarkably similar to what we observe in galaxy surveys, providing strong confirmation that our understanding of structure formation is fundamentally correct. Questioning our assumptions as we drift through our exploration of why the universe is bigger than it should be, let us pause and consider the assumptions that underlie our cosmological models, for it is possible that some of these assumptions are wrong or incomplete, and that this is the source of the paradox. One fundamental assumption is that the universe is homogeneous and isotropic on large scales, meaning that it looks the same on average in all directions and at all locations. But this assumption might not be exactly correct. We might live in a region that is atypical, denser, or less dense than average. And this could affect our measurements of the expansion rate and of distances to distant objects. Another assumption is that general relativity correctly describes gravity on cosmic scales. But perhaps gravity behaves differently over very large distances or very long times than Einstein's theory predicts. and this modified gravity could affect the expansion rate without requiring dark energy. Yet another assumption is that the fundamental constants of nature, things like the speed of light and the strength of gravity and the masses of elementary particles, are truly constant, unchanging over cosmic time. But if any of these constants have changed slowly over billions of years, it could affect our interpretation of observations and lead to incorrect conclusions about the size and age and expansion rate of the universe. Each of these possibilities has been explored to some extent by researchers. And while none has emerged as a clearly favored alternative to the standard model, they remind us that science progresses by questioning assumptions and by remaining open to the possibility that our current understanding is incomplete. The limits of knowledge. Let us drift into a more philosophical realm now, considering the fundamental limits to what we can know about the universe and whether some questions might be forever beyond our ability to answer. The observable universe has a finite size, limited by the distance that light has been able to travel since the Big Bang, and anything beyond this horizon is fundamentally inaccessible to us, at least as long as the laws of physics as we understand them hold. This means that if the universe is much larger than the observable universe, we can never directly observe most of it, never know for certain what lies beyond our horizon. Similarly, if the multiverse exists and our universe is just one bubble among countless others, we might never be able to observe or interact with the other universes, making the multiverse hypothesis difficult or impossible to test scientifically. There are also limits imposed by the nature of information itself. For in a universe governed by quantum mechanics, there are inherent uncertainties that cannot be eliminated no matter how carefully we measure. And in a universe where space is expanding and accelerating, there are limits to how much information we can gather before distant regions recede beyond our reach. These limits are not merely technological, not problems that could be solved with better telescopes or more powerful computers, but are fundamental constraints imposed by the structure of space-time and the laws of physics. Recognizing these limits does not mean we should stop exploring or stop asking questions, but it does encourage a certain humility, an acknowledgement that the universe might contain mysteries that will forever remain beyond human comprehension. And perhaps that is part of what makes the cosmos so fascinating. The beauty of uncertainty. As we continue our gentle drift through the cosmos, let us appreciate that uncertainty and mystery are not failures of science, but are essential features of the scientific process. For science progresses not by finding final answers, but by asking better questions and by refining our understanding through observation and experimentation. The question of why the universe is bigger than it should be is a perfect example of this process. For it emerges from careful measurements that reveal a discrepancy between observation and theory. And this discrepancy drives new research, new observations, new theoretical ideas, pushing the boundaries of knowledge outward. If we already had all the answers, if the universe held no more surprises, science would be complete and there would be nothing left to discover. But the reality is that every answer raises new questions. Every solved mystery reveals deeper mysteries. And this endless frontier is what makes cosmology and science in general so exciting. The paradox of cosmic size reminds us that the universe is not required to make sense to us, not required to fit neatly into our theories and models. And when observations conflict with predictions, it is the theories that must change, not the observations. This willingness to follow the evidence wherever it leads, even when it contradicts cherished ideas or requires uncomfortable conclusions, is one of the great strengths of the scientific method. And it is why science has been so successful at uncovering the workings of nature, despite the countless ways in which nature could have remained forever mysterious. The scale of the mystery. Let us step back now and appreciate the sheer scale of the mystery we have been exploring. For the question of why the universe is bigger than expected is not a small technical puzzle, but touches on the most fundamental aspects of existence, on the origin and fate and structure of everything that is. The universe spans at least 93 billion light-years across the observable portion alone, possibly infinite beyond that, containing at least 2 trillion galaxies each with hundreds of billions of stars. And yet we find that this enormous cosmos is governed by relatively simple laws that can be written in mathematical equations that fit on a single page. And this simplicity underlying complexity is one of the great wonders of nature. The expansion of the universe, the phenomenon that creates our size paradox, is itself an astonishing fact. For it means that space is not a fixed stage on which events play out, but is a dynamic entity that grows and changes, carrying matter and energy along with it. And this expansion connects the smallest quantum fluctuations in the earliest moments of the Big Bang to the largest structures visible in the cosmos today. The fact that we can understand anything at all about the universe on these scales, that we can make measurements and predictions and test theories about events that occurred billions of years ago and billions of light years away, is a testament to the power of human curiosity and intellect. And it should fill us with wonder and with gratitude for the opportunity to live in a time when such knowledge is possible. Returning to the present moment, as we prepare to drift back from the cosmic scales we have been exploring, returning gently to the human scale and to the present moment, let us carry with us the sense of perspective that cosmology provides. When we contemplate the vastness of the universe and the strangeness of its expansion and the mysteries that remain unsolved, our everyday concerns can seem small and temporary. And this can be either unsettling or comforting, depending on how we approach it. The cosmos does not care about our worries and anxieties, does not notice our struggles or triumphs. And yet this indifference is not cruel, but simply is a fact of existence that we can choose to find either meaningless or liberating. Knowing that the universe is billions of years old and billions of light years across, that it contains wonders beyond counting and mysteries beyond current understanding, can help us appreciate the brief and precious nature of our own existence. The miraculous fact that we are here at all, able to think and feel and wonder, able to look up at the night sky and ask questions about what we see. The paradox of a universe that is bigger than it should be reminds us that reality is stranger than we imagine. That the cosmos is under no obligation to conform to our expectations, and that the pursuit of understanding is a journey without end, always revealing new horizons. The whisper of gravitational waves let us drift now into a different way of observing the universe, a method that does not rely on light or any form of electromagnetic radiation, but instead listens to the ripples in space-time itself. The gravitational waves that carry information about some of the most violent and energetic events in the cosmos. Gravitational waves were predicted by Einstein's general theory of relativity over a century ago, emerging naturally from the mathematics that describes how mass and energy curve space-time. For just as accelerating electric charges produce electromagnetic waves, accelerating masses produce gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light. For decades, these waves remained purely theoretical, too weak to detect with any conceivable instrument. For even the most violent cosmic events produce gravitational waves that stretch and compress space by amounts smaller than the diameter of an atomic nucleus over distances of several kilometers. But in 2015, after decades of development and refinement, the LIGO gravitational wave observatories in the United States succeeded in detecting gravitational waves for the first time. observing the merger of two black holes more than 1 billion light-years away. An event that released more energy in a fraction of a second than all the stars in the visible universe combined. Though most of that energy was in the form of gravitational waves rather than light. Since that first detection, dozens more gravitational wave events have been observed. Black holes merging with other black holes, neutron stars colliding and merging. Each event providing new information about these extreme objects and about the nature of space-time itself. Gravitational waves are particularly valuable for cosmology because they provide an independent way to measure distances across the universe. A method that does not rely on the cosmic distance ladder or on standard candles like supernovae. When two neutron stars merge, the gravitational waves they produce have an amplitude that depends on the distance to the merger. And if the merger also produces light and other electromagnetic radiation, allowing us to identify which galaxy it occurred in and measure that galaxy's redshift, then we can determine both the distance and the recession velocity independently, providing a direct measurement of the Hubble constant without needing intermediate steps. The first such measurement was made in 2017 when LIGO and its European counterpart Virgo detected gravitational waves from a neutron star merger that was also observed by dozens of telescopes around the world. And the distance and redshift measurements from this event gave a Hubble constant of about 70, right in between the values obtained from the cosmic microwave background and from the supernova distance ladder. Though with large uncertainty due to the difficulty of measuring the properties of gravitational waves precisely. As more neutron star mergers are detected and as the gravitational wave detectors become more sensitive, allowing them to observe events farther away and with better precision. Gravitational wave measurements of the Hubble constant will become increasingly important for resolving the Hubble tension and for understanding why the universe appears bigger than it should be. Gravitational waves also offer the possibility of observing the universe at times and in ways that are impossible with light. For gravitational waves can pass through matter almost without interacting, traveling unimpeded from their source to our detectors, while light is easily absorbed or scattered. This means that gravitational waves could potentially allow us to observe events in the very early universe, moments after the Big Bang, when the cosmos was still opaque to light, and to test theories about inflation and the origin of the universe in ways that are not possible with electromagnetic observations alone. There are even proposals for space-based gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, which would orbit the Sun and observe gravitational waves at lower frequencies than ground-based detectors can access. Frequencies produced by supermassive black hole mergers and by other exotic sources. And these observations could reveal new phenomena that we have not yet imagined, and could help resolve mysteries about how supermassive black holes formed and how galaxies evolved. The era of gravitational wave astronomy is still in its infancy, with new discoveries being made regularly and with the technology continuing to improve. And as we drift through the next few decades, gravitational waves will likely transform our understanding of the cosmos just as dramatically as optical and radio telescopes did in previous generations, providing new windows onto the universe and revealing aspects of reality that have been hidden from us until now. And perhaps, just perhaps, these new observations will help us understand why the universe is bigger than our current theories predict. Or they will reveal new mysteries that make the cosmos seem even stranger and more wondrous than we currently imagine. The problem of initial conditions. As we float gently through the landscape of cosmological puzzles, let us consider one of the most profound questions that underlies much of what we have been discussing. The question of initial conditions, of why the universe began with the particular properties it had, and whether those properties were inevitable or arbitrary, or fine-tuned for some purpose. When we trace cosmic history backward through time, running the expansion in reverse and watching the universe become smaller and denser and hotter, we eventually reach a point where our current theories break down. A moment called the Planck time, about 10 to the minus 43 seconds after the Big Bang, when the density and temperature were so extreme that quantum effects of gravity become important, and we do not have a theory that can properly describe what happens. Before this moment, or perhaps at this moment if there is no before, the initial conditions of the universe were set. The amount of matter and energy, the strength and nature of the fundamental forces, the pattern of quantum fluctuations that would eventually become galaxies. All of this was somehow determined, and understanding how and why is one of the deepest questions in all of physics. The standard Big Bang model simply takes the initial conditions as given, starting the clock at some early time when the universe was already expanding and cooling. And it makes no attempt to explain why those particular conditions existed rather than some other conditions. But this lack of explanation is unsatisfying to many physicists, for it seems to push the question of origin back without really answering it. Inflation provides a partial answer by showing that many features of the universe that seem finely tuned, like the flatness of space and the uniformity of the cosmic microwave background, can emerge naturally from a period of rapid expansion, regardless of what the conditions were before inflation. But inflation itself requires certain initial conditions, a region of space where the inflaton field has the right value to drive exponential expansion. And we still must ask where those conditions came from. Some theorists have proposed that the universe as a whole might be eternal, that the Big Bang was not the beginning of time, but merely a transition from some previous state, perhaps a contracting universe that bounced and began expanding again, or a universe that undergoes endless cycles of expansion and contraction, each cycle ending in a big crunch that becomes the Big Bang of the next cycle. And in such models, the question of initial conditions is replaced by the question of what maintains these cycles and whether they have been going on forever or had some ultimate beginning. Other theorists have explored the idea that the universe emerged from nothing, that quantum mechanics allows for the spontaneous creation of space-time and matter and energy from a quantum vacuum state. And while this sounds paradoxical, for how can something come from nothing? Quantum field theory does indeed allow for particles to appear and disappear from vacuum fluctuations, and some versions of quantum gravity suggest that entire universes could emerge in a similar way, tunneling out of nothingness in a quantum event. These ideas push at the boundaries of what physics can meaningfully discuss, for concepts like time and causation and existence become ambiguous when we try to apply them to the origin of the universe itself. And it is not clear whether questions about what happened before the Big Bang even make sense, or whether time itself only exists within the universe rather than extending beyond it. The question of initial conditions also connects to the anthropic principle, the observation that the universe must have properties compatible with the existence of observers like us. For if the initial conditions had been very different, if the strength of gravity or the mass of the electron or countless other parameters had values even slightly different from what they are, then stars and planets and life might never have formed, and there would be no one to observe the universe and ask why it has the properties it does. In a multiverse where different regions have different properties, we necessarily find ourselves in a region where the conditions allow for our existence. And this might be the only explanation for why the universe has the particular initial conditions it does. Not because they are special or inevitable, but simply because we could not exist in universes with different conditions. And this anthropic reasoning, while it provides a kind of answer, is philosophically troubling to many scientists because it seems to give up on finding a deeper explanation and to accept that some features of the universe might be matters of chance rather than products of fundamental laws. The texture of space-time itself, let us drift deeper now into the very fabric of reality, into the question of what space and time actually are at the most fundamental level. For our understanding of why the universe is bigger than it should be depends critically on our understanding of space-time itself. And yet, space-time remains in many ways mysterious, particularly when we try to probe its properties at the smallest scales or in the most extreme conditions. In Einstein's general relativity, space-time is a smooth, continuous manifold, a mathematical structure that can be curved and warped by matter and energy, but that has no fundamental graininess or discreteness. And this smooth space-time is the arena in which all physical processes occur, the stage on which the cosmic drama unfolds. But quantum mechanics suggests that nothing in nature is truly continuous at the smallest scales. That everything from energy to angular momentum comes in discrete packets called quanta. And if this applies to space-time itself, then space and time might not be smooth continua, but might have some fundamental granular structure, a minimum length scale below which the concepts of distance and duration lose their usual meanings. This hypothetical granularity is expected to appear at the Planck scale, distances of about 10 to the minus 35 meters and times of about 10 to the minus 43 seconds. Scales that are so tiny compared to anything we can measure directly that they seem more like abstract mathematical constructs than physical realities. And yet at these scales, according to our best theoretical understanding, space-time itself should become a quantum entity, subject to fluctuations and uncertainties, potentially even forming a kind of foam where the topology of space is constantly changing, wormholes and baby universes appearing and disappearing in a seething quantum chaos. Understanding the quantum nature of space-time is the goal of quantum gravity, a theory that would unify general relativity and quantum mechanics, two of the most successful theories in physics that nonetheless seem fundamentally incompatible with each other. For general relativity treats space-time as a smooth classical background, while quantum mechanics requires that everything be subject to quantum uncertainties and fluctuations. Many approaches to quantum gravity have been proposed over the decades, string theory being perhaps the most famous, which suggests that the fundamental constituents of reality are not point particles, but tiny one-dimensional strings whose different vibration patterns correspond to different particles. And in string theory, space-time emerges as a kind of collective behavior of strings rather than being fundamental. And the theory requires additional dimensions beyond the three of space and one of time that we experience. Dimensions that are curled up so small that we do not notice them, but that nonetheless affect the properties of particles and forces. Another approach is loop quantum gravity, which attempts to quantize space-time directly, describing it as a network of loops and nodes at the Planck scale, with space itself being made of discrete quantum units of volume. And in this picture, the smooth space-time of general relativity is an approximation that emerges when we look at scales much larger than the Planck scale, just as a smooth-looking photograph is actually made of discrete pixels when examined closely. Neither string theory nor loop quantum gravity has yet made testable predictions that would allow us to determine which, if either, is correct. And both face significant mathematical and conceptual challenges. But they represent humanity's best current attempts to understand what space-time is at the deepest level. The question of space-time's nature is not just an abstract theoretical concern, but has direct implications for cosmology and for understanding the expansion of the universe. For if space-time has quantum properties, then the expansion itself might be subject to quantum fluctuations, and the relationship between distance and time might be more subtle than we currently understand, potentially affecting how we measure cosmic distances and how we interpret observations of distant galaxies. Some speculative ideas even suggest that the acceleration of the expansion, the dark energy that makes the universe bigger than expected, might be related to quantum properties of space-time, perhaps arising from the accumulation of quantum vacuum fluctuations over cosmic scales. Though making this idea work quantitatively has proven extremely difficult and requires new physics beyond our current understanding. And so we drift here at the edge of knowledge, where established theory gives way to speculation and where the questions outnumber the answers by a vast margin. Alternative cosmologies and modified gravity. As we continue our gentle drift through the space of ideas, let us consider that perhaps the paradox of a universe bigger than expected arises not from dark energy or measurement errors, but from a more fundamental problem with our cosmological models. A possibility that some researchers have explored by developing alternative cosmologies that modify or replace aspects of the standard Big Bang model. One class of alternatives involves modifying general relativity itself, proposing that gravity works differently on very large scales than Einstein's theory predicts. And if these modifications are chosen carefully, they can potentially explain observations like the acceleration of cosmic expansion without needing to invoke dark energy. These modified gravity theories typically add new terms to Einstein's equations, terms that become important only when dealing with very weak gravitational fields or very large distances. And they can be constructed to reproduce all the successful predictions of general relativity in well-tested regimes like the solar system and binary pulsars, while giving different predictions for cosmology. One such theory is called Fauché-R gravity, which modifies the Einstein-Hilbert action that underlies general relativity by replacing the Ricci scalar r with some function er. And depending on the choice of function, this can lead to accelerated expansion without dark energy. Though most versions of FR gravity face challenges in matching all observations simultaneously, and in avoiding other problems like instabilities or violations of constraints from solar system tests. Another approach is called massive gravity, which proposes that the graviton, the hypothetical particle that mediates the gravitational force, has a small mass rather than being exactly massless, as general relativity assumes. And this small mass would modify gravity on the largest scales, potentially explaining cosmic acceleration. Though massive gravity theories have their own technical difficulties related to maintaining consistency and avoiding ghost particles that would make the theory unstable. Beyond modified gravity, some researchers have explored entirely different frameworks for cosmology, questioning whether the Big Bang model itself is correct, or whether it might need to be replaced by something fundamentally different. One alternative is the steady-state cosmology, which was popular in the mid-20th century before being largely abandoned after the discovery of the cosmic microwave background, and which proposed that the universe has always existed in roughly its current state, with new matter being continuously created to fill the space opened up by expansion, maintaining a constant density over time. Steady-state cosmology is now disfavored because it cannot explain the cosmic microwave background or the observed evolution of galaxies and quasars. But it illustrates that alternatives to the Big Bang are possible in principle. Another alternative that has received some attention is plasma cosmology, which suggests that electromagnetic forces and plasma physics play a more important role in shaping the universe than standard cosmology allows. Though this approach has not been able to explain key observations like the cosmic microwave background or the abundance of light elements. More recently, some theorists have explored cyclic cosmologies, where the universe undergoes repeated cycles of expansion and contraction, with each big crunch transitioning into a big bang that starts a new cycle. And in some versions of these models, the properties of the universe can change from cycle to cycle, potentially providing a mechanism for explaining why our current universe has the particular properties it does. These cyclic models face challenges in explaining how information or structure can survive the transition from one cycle to the next, for the extreme conditions near a big crunch would seem to erase all memory of what came before. But some clever mechanisms have been proposed involving extra dimensions or special fields that can carry information across the transition. As we drift through these alternative ideas, it is important to remember that while the standard cosmological model has been remarkably successful in explaining a wide range of observations, from the cosmic microwave background to the large-scale structure of galaxies to the abundance of light elements, science always remains open to new ideas and new evidence. And if observations continue to suggest that the universe is bigger than the standard model predicts, then perhaps one of these alternatives, or something entirely new that we have not yet imagined, will eventually replace the standard model and provide a better explanation for what we observe. The human element in cosmic measurement. Let us drift now into a different aspect of the mystery, considering the role that human observation and interpretation play in creating the paradox of a universe bigger than expected. For cosmology is not just about the universe itself, but also about how we measure and understand it. And the tools and methods we use can introduce biases and uncertainties that affect our conclusions. Every measurement in astronomy involves a chain of assumptions and calibrations, from the detectors that capture photons to the analysis methods that extract information from the data to the theoretical models that relate observations to physical properties. And at each step in this chain, there is potential for systematic errors, mistakes or biases that affect the results in consistent ways rather than being random fluctuations that average out with more data. In the context of measuring the Hubble constant and cosmic distances, systematic errors could arise from many sources, from uncertainties in the distances to nearby galaxies that anchor the distance ladder to possible variations in the intrinsic brightness of Type Ia supernovae to contamination of supernova samples by other types of transient events that are mistakenly identified as Type Ia supernovae. The Hubble tension, the discrepancy between different measurements of the expansion rate, could potentially be explained by systematic errors in one or more measurement methods. Though after decades of careful work by many independent research groups, no such error has been convincingly identified, and the tension has persisted and even grown as measurements have become more precise. The human element extends beyond technical measurement issues to include the psychological and sociological aspects of how science is done. For scientists are human beings with preconceptions and biases and career pressures. And these factors can influence which research directions are pursued and which results are published and which ideas gain acceptance. In cosmology, there is a natural tendency toward conservatism, toward explaining new observations within the existing framework rather than proposing radical alternatives of bases. And this conservatism is generally healthy because the existing framework has been successful and because extraordinary claims require extraordinary evidence. But it also means that truly revolutionary ideas might be resisted or overlooked, especially if they come from outside the mainstream or if they challenge deeply held assumptions. The history of science is full of examples where the correct explanation for a phenomenon was initially rejected because it seemed too strange or because it contradicted established theory. From continental drift in geology to the existence of meteorites, to the role of bacteria in ulcers. And while most rejected ideas are indeed wrong, occasionally the mavericks are right and the establishment is wrong. The question of whether the universe is bigger than expected might be one of these cases where the answer requires thinking outside the conventional framework, or it might be a case where careful systematic work within the conventional framework eventually resolves the tension and shows that our understanding was correct all along, but that some subtle effect was being missed. As we drift through these considerations of the human element in science, we can appreciate that cosmology, despite dealing with the most impersonal and vast subjects imaginable, is fundamentally a human endeavor, carried out by people with all their strengths and limitations. And this human dimension is part of what makes science both challenging and beautiful. For it means that progress requires not just clever instruments and mathematical skill, but also creativity and persistence and the willingness to question even cherished ideas when the evidence demands it. The universe may be bigger than it should be according to our current theories, or our measurements may be subtly wrong, or we may need to revise our understanding of how measurement relates to reality. But whatever the resolution turns out to be, it will emerge from the collective work of many scientists over many years, each contributing their piece to the puzzle, and the path to understanding will be winding and uncertain, with false starts and dead ends along the way. But this is how science has always worked, and it is how we will eventually understand this mystery too. Drifting into sleep. As you sink deeper into relaxation, feeling your body becoming heavier and more relaxed with each breath, let yourself drift like a galaxy in the expanding cosmos, carried along by forces larger than yourself, moving without effort through the darkness toward rest. The question of why the universe is bigger than it should be can float away now, becoming just another thought, dissolving into the background of your mind. No more important or urgent than any other passing thought. Just information that your brain will process and integrate while you sleep. Sleep is its own kind of mystery, its own expansion into an inner cosmos, where dreams take the place of galaxies and where consciousness explores territories that have no physical location. And this inner universe is as worth exploring as the outer one, though in different ways and for different purposes. Let your breathing become the rhythm of cosmic expansion, slow and steady and inexorable. Each exhale releasing a little more tension, each inhale bringing calm. And as you breathe, feel yourself expanding into the space around you, your boundaries becoming softer and less defined, until there is no clear distinction between you and the air and the room and the night. You are safe and comfortable and supported, held by gravity just as galaxies are held in their clusters, connected to everything through invisible forces. Part of a universe that is bigger than it should be and more mysterious than we can fully comprehend. And this is beautiful. This is right. This is exactly as it should be. Rest now in the expanding darkness. Let yourself be carried by the gentle tide of sleep into whatever dreams may come, knowing that the universe will still be here when you wake, still expanding, still mysterious, still inviting wonder, and that you are part of it all, a small but essential thread in the vast cosmic web, a point of consciousness in the infinite expanse, a moment of awakening in the eternal night, and now a moment of rest, of peace, of drifting, of sleep. The eternal dance of mystery and understanding as we drift toward the conclusion of our journey through the cosmos, floating gently through the vast darkness that surrounds us on all sides. Let us gather together all the threads we have been following, all the mysteries and paradoxes and questions that have accompanied us through this long, peaceful night. and let us weave them into a final contemplation of what it means to exist in a universe that is bigger than it should be. What this paradox tells us about reality and about ourselves and about the eternal human quest to understand the cosmos we inhabit. We began our journey by ascending from Earth, leaving behind the familiar world of everyday experience and rising through layers of atmosphere into the darkness of space. And as we rose, we encountered the first surprise. The discovery made by Edwin Hubble nearly a century ago that the universe is not static, but expanding. That galaxies are rushing away from each other, carried by the stretching of space itself. And this discovery transformed our understanding of the cosmos, revealing that the universe has a history. That it began in a hot, dense state we call the Big Bang, and has been expanding and cooling ever since, evolving from simplicity to complexity, from uniformity to structure, from a featureless plasma to a cosmos filled with galaxies and stars and planets, and on at least one planet that we know of, with life and consciousness and the ability to look back across billions of years and understand something of where we came from. The expansion of space is itself a strange and beautiful phenomenon, difficult to grasp intuitively because our everyday experience does not include anything like it. For we are used to objects moving through space, but not to space itself changing, growing, carrying objects along with it like leaves floating on a stream. And yet this is what is happening on the largest scales. Galaxies separating from each other not because they are moving, but because the space between them is increasing. And this expansion affects everything we observe when we look at distant objects, stretching the wavelength of light from them toward the red end of the spectrum, making distant galaxies appear redder than they would if they were nearby, and allowing us to measure how fast they are receding by measuring this redshift. When astronomers measured the redshifts of many galaxies at different distances, they discovered Hubble's law, the relationship between distance and recession velocity that tells us about the rate of cosmic expansion. And this relationship is characterized by a number called the Hubble constant, which has been one of the most important quantities in cosmology for decades. For it tells us not just about the current expansion rate, but also about the age of the universe and about its ultimate fate, whether it will expand forever or eventually recollapse. Measuring the Hubble constant precisely has proven to be remarkably difficult, requiring careful observations of distances to galaxies using methods like Cepheid variable stars and Type Ia supernovae. And as these measurements have become more and more precise over the past few decades, a puzzling discrepancy has emerged, what cosmologists call the Hubble tension. For different methods of measuring the Hubble constant give slightly different results, with some methods suggesting a value around 67 kilometers per second per megaparsec, and other methods suggesting a value around 73. And this difference of about 10% may not sound like much, but it is statistically significant, and it has persisted despite intensive efforts to find and correct any systematic errors that might explain it. This tension is directly related to the paradox we have been exploring, the question of why the universe is bigger than it should be. For if the expansion rate is higher than some measurements suggest, then the universe has had time to grow larger than we would expect, making distant galaxies appear farther away than simple calculations would predict. And this discrepancy could be telling us something important about the cosmos, perhaps revealing new physics that our current theories do not include, or perhaps pointing to subtle measurement issues that we have not yet fully understood. The discovery in the late 1990s that the expansion of the universe is not slowing down as expected, but is actually accelerating, speeding up over time rather than being gradually braked by gravity, added a new dimension to this mystery. For acceleration implies the existence of something entirely unexpected, a form of energy that fills all of space and that acts as a kind of repulsive force, pushing space to expand faster and faster. And this dark energy, as it has come to be called, is now thought to make up about 68% of the total energy content of the universe. Far more than ordinary matter or even dark matter, making it the dominant component of the cosmos, even though we have no idea what it is or why it exists. The simplest explanation for dark energy is that it is the cosmological constant, Einstein's old idea of a constant energy density of empty space itself. But if this is correct, then we are faced with another profound mystery. For quantum field theory predicts that empty space should have energy due to quantum vacuum fluctuations. But the predicted value is about 10 to the 120 times larger than what we observe, an enormous discrepancy that represents one of the deepest unsolved problems in theoretical physics. The cosmological constant problem asks why the vacuum energy is so small, or, equivalently, why the cosmological constant is so small. And no satisfactory answer has been found, despite decades of work by some of the best theoretical physicists in the world. And this suggests that we are missing something fundamental in our understanding of quantum mechanics, or gravity, or both. Some principle or mechanism that we have not yet discovered that explains why the vacuum energy has the particular tiny value that we observe, rather than being enormously larger or exactly zero. As we have drifted through our exploration, we have encountered many other aspects of this central mystery. The role of dark matter in shaping the structure of the universe and in affecting the expansion through its gravitational pull. The importance of the cosmic microwave background radiation as a snapshot of the early universe that allows us to test cosmological models with remarkable precision. The theory of cosmic inflation, which proposes a brief period of exponential expansion in the first moments after the Big Bang to explain why the universe is so uniform and so flat. The possibility of a multiverse where our universe is just one of countless others, each with different properties. The insights provided by gravitational wave astronomy, which offers a new way to measure cosmic distances independent of the traditional distance ladder. The questions about the nature of space-time itself and whether it is continuous or discrete at the smallest scales. The possibility that general relativity needs to be modified on cosmic scales to explain observations without dark energy. And the human element in scientific measurement and interpretation, which reminds us that cosmology is not just about the universe, but also about how we observe and understand it. Each of these topics could be explored at far greater length than we have done tonight. Could fill entire books or courses or careers. For cosmology is a vast field, touching on physics and astronomy and mathematics and philosophy, drawing on observations from the largest telescopes and experiments at the highest energies and calculations of enormous complexity. And yet all of this effort is directed toward answering some of the most basic questions that humans have asked for as long as we have been able to ask questions. Where did we come from? How did the universe begin? What is it made of? How does it work? Where is it going? And why is it the way it is rather than some other way? The fact that we can make progress on these questions at all is remarkable. For we are tiny creatures living on a small planet orbiting an ordinary star in an ordinary galaxy, in a universe containing hundreds of billions of galaxies. And yet, we have been able to figure out that the universe is expanding, that it began in a Big Bang nearly 14 billion years ago, that it is filled with dark matter and dark energy that we cannot see directly, but whose effects we can measure, that it went through a period of cosmic inflation that set the initial conditions for everything that followed, and that it will continue expanding forever, eventually becoming a cold, dark, empty place where nothing interesting ever happens again. These achievements represent the culmination of centuries of scientific work, building on the observations and insights of countless individuals from Galileo, who first turned a telescope to the heavens, to Hubble, who discovered cosmic expansion, to Penzias and Wilson, who discovered the cosmic microwave background, to the teams who discovered dark energy. And this accumulated knowledge is one of the great treasures of human civilization, a testament to what we can accomplish when we combine careful observation with mathematical reasoning, and when we follow the evidence wherever it leads, regardless of whether the conclusions are comfortable or intuitive. But as impressive as our achievements are, we must also acknowledge how much we do not know. How many mysteries remain unsolved? How many questions we cannot yet answer? We do not know what dark matter is, despite decades of searching for particles that might compose it. We do not know what dark energy is, or why it has the value it does. We do not know whether inflation really happened, or what drove it if it did. We do not know whether the universe is finite or infinite in extent. We do not know whether there are other universes, or whether ours is unique. We do not know how to reconcile quantum mechanics with general relativity, or what space-time is like at the smallest scales. We do not know why the universe has the particular laws of physics it does, or whether those laws could have been different. We do not know whether the Hubble tension represents new physics or subtle measurement issues. We do not know, ultimately, why the universe is bigger than it should be according to our current theories. And this not knowing is not a failure, but is the very essence of science. For science progresses by identifying what we do not understand and then working to understand it. And the existence of unsolved mysteries is what drives scientific research forward and what makes science exciting and vital. The paradox of cosmic size, the question that has been our companion throughout this journey, is a perfect example of how science works, for it emerges from the tension between different measurements and different theoretical expectations. And this tension tells us that something interesting is happening, that either our measurements need refinement or our theories need modification, or both. And resolving this tension will require new observations and new ideas and new ways of thinking about the cosmos. And when it is finally resolved, whether that happens next year or in a decade or longer, we will understand something new about the universe. And that new understanding will almost certainly raise new questions that we have not yet thought to ask. As we drift through these reflections on the state of cosmology and on the paradox of a universe bigger than expected, we can step back even further and consider what this all means in a broader philosophical sense. What it tells us about the nature of reality and about our place in it. The universe is vast beyond human comprehension, containing more stars than grains of sand on all the beaches of Earth, stretching across distances so enormous that light takes billions of years to cross them, existing for a span of time that makes all of human history seem like less than a blink of an eye. And yet this vast ancient cosmos has given rise to beings capable of understanding something of its nature. Beings who can look up at the night sky and recognize that those tiny points of light are distant suns like our own. Who can measure the expansion of space and trace the history of the universe back to its beginning. Who can ask why the universe is bigger than expected and work to find the answer. This ability to understand is itself one of the great mysteries. For there is no obvious reason why the universe should be comprehensible to human minds. Why the patterns and structures we see should be describable by mathematics. Why the laws of physics should be consistent and simple enough that creatures with brains evolved to hunt and gather. On the African savanna can figure them out and use them to predict phenomena we have never directly experienced. The physicist Eugene Wigner once wrote about the unreasonable effectiveness of mathematics in the natural sciences, pointing to the strange fact that mathematical structures invented by pure mathematicians with no thought of practical application often turn out to describe physical phenomena with remarkable accuracy. And this effectiveness suggests some deep connection between the structure of our minds and the structure of reality. A connection that we do not fully understand, but that makes science possible. The fact that the universe can be understood, at least partially and approximately, suggests that there is an order to nature, patterns and regularities that persist across time and space. And finding these patterns is what science is fundamentally about. Whether we are studying the expansion of the cosmos, or the behavior of subatomic particles, or the evolution of life, or the workings of the human mind. The paradox of a universe bigger than expected is just one small part of this larger, pattern-seeking endeavor. One thread in the vast tapestry of human knowledge. But it is a thread that connects to many others. For understanding cosmic expansion requires understanding gravity and space-time and quantum mechanics and thermodynamics and much else. And progress on this question will likely illuminate other questions and perhaps raise new ones. And this interconnectedness of knowledge is one of the beautiful features of science. The way that insights in one area can have implications for seemingly unrelated areas. As we float here in the darkness, contemplating the mystery of cosmic size, we can also appreciate the aesthetic dimension of cosmology. For there is a beauty in the equations that describe the expansion of the universe, in the elegant simplicity of Einstein's field equations that relate the curvature of space-time to the distribution of matter and energy. In the way that the entire history of the cosmos can be traced from a few initial conditions and a handful of fundamental constants. In the images of distant galaxies and nebula captured by telescopes that reveal structures of stunning intricacy and variety. This beauty is not incidental, but is often taken as a guide by theoretical physicists who seek equations that are not just correct, but elegant, that have a certain mathematical harmony and simplicity. For experience has shown that the most successful theories tend to be beautiful in this mathematical sense. And ugliness or excessive complexity in a theory is often a sign that something is wrong, that the theory is patched together rather than being a natural description of reality. The quest to understand why the universe is bigger than expected is part of humanity's broader quest to understand nature, to find order in apparent chaos, to discover the principles that govern reality. And this quest has both practical and spiritual dimensions. The practical dimension is obvious. For understanding the universe has led to technologies that have transformed human life. From the GPS satellites that rely on general relativity to the nuclear power and nuclear weapons that rely on Einstein's equation, E equals mc squared, to the medical imaging techniques that rely on quantum mechanics, to the computers and smartphones and internet that rely on solid-state physics and semiconductor theory. And while cosmology may seem like a purely academic pursuit with no practical applications, the techniques and technologies developed for cosmological observations often find uses elsewhere. And the fundamental knowledge we gain about physics from studying the cosmos may someday lead to applications we cannot now imagine. But beyond the practical applications, the quest for understanding has a spiritual dimension. A sense of wonder and awe at the majesty of the cosmos and at our ability to comprehend even a small part of it. And this sense of wonder is valuable in itself, enriching our lives and giving us perspective on our place in the grand scheme of things. And this is why people who will never work in science or use scientific knowledge in their daily lives still care about whether the universe is expanding, or what happened at the Big Bang, or whether there are other universes. For these questions touch on deep human needs to understand where we came from and what our existence means. The paradox of a universe bigger than expected is not just a technical problem for professional cosmologists to solve. but is a window into the mystery of existence itself. A reminder that reality is stranger and more wonderful than our everyday experience suggests. That the cosmos is not just a backdrop for human affairs, but is a dynamic, evolving entity with its own history and destiny. And that we are part of this cosmic story, made of atoms forged in ancient stars, shaped by billions of years of evolution, capable of contemplating our origins and our future and finding meaning and beauty in the process. As we prepare to complete our journey, drifting gently back toward the everyday world and toward the rest that awaits at the end of this long night, let us carry with us not just the specific facts and ideas we have encountered, not just the numbers and equations and theories, but more importantly, the sense of wonder and mystery that cosmology evokes. The recognition that we live in a universe far larger and older and stranger than our ancestors ever imagined. A universe that contains mysteries we have not yet solved and perhaps mysteries we have not yet discovered. A universe that is, in some profound sense, bigger than it should be. Whether that means bigger than our theories predict, or bigger than our minds can fully grasp, or simply bigger than, seems reasonable given the brief span of human life and the limited scope of human experience. This bigness is not a problem to be solved, but a reality to be appreciated. An invitation to humility and to wonder. A reminder that we are small parts of something vast, and that our understanding, impressive as it is, remains incomplete and probably always will. For the universe is under no obligation to reveal all its secrets to us. And some mysteries may remain forever beyond our reach, and yet the pursuit of understanding is worthwhile, even if complete understanding is impossible. For the journey is as valuable as the destination, and the questions we ask are as important as the answers we find. Let yourself rest now in this embrace of mystery, in the acceptance that the universe is bigger than we expected and perhaps bigger than we can ever fully understand. And let this vastness be not frightening, but comforting. For it means that there is always more to discover, always new horizons to explore, always room for wonder and for growth. As you lie there in comfort, your breathing slow and steady, your body relaxed and supported, let the concepts and images from tonight's journey begin to fade into the background of your awareness, becoming softer and less distinct like stars disappearing into the dawn. For you do not need to remember every detail, do not need to hold on to every fact, but can simply allow the experience to settle into your mind, where it will be processed and integrated during sleep, becoming part of the rich tapestry of your understanding, contributing to your sense of the world and your place in it, in ways that you may not consciously recognize, but that will influence how you think and feel and see the cosmos. The universe will still be expanding tomorrow, still accelerating under the influence of dark energy, still posing the puzzle of why it is bigger than expected. And scientists will still be working on the problem, making new observations, developing new theories, gradually assembling the pieces of the puzzle. But for now, in this moment, you can let it all go, can release any need to understand or figure out or solve, can simply be at peace with the mystery. The expansion of space will continue whether you think about it or not. Dark energy will keep pushing galaxies apart. The Hubble tension will remain unresolved until someone figures it out. And all of this will happen without requiring anything from you, without needing your attention or concern or worry, and this is a profound relief. The recognition that the cosmos takes care of itself, that the vast, impersonal forces of nature operate according to laws that do not depend on human observation or understanding, that the universe was here long before we arrived and will be here long after we are gone, and that in this moment, right now, you are free to simply rest, to let your mind become quiet and still, to allow sleep to come naturally and easily like night following day. As you drift deeper into relaxation, feel yourself becoming part of the expansion, your consciousness spreading out like space itself, your thoughts becoming more diffuse and widely separated, the boundaries between you and the darkness around you dissolving until you are not separate from the universe, but are the universe experiencing itself. One small localized pattern of complexity in the vast sea of being. A brief moment of awareness in the eternal dance of matter and energy. And this is enough. This is beautiful. This is exactly as it should be. The universe is bigger than it should be, and so are you, bigger than you think you are, connected to everything through forces seen and unseen. Part of a story that stretches from the Big Bang to the far future. A story that includes the formation of atoms in ancient stars, and the assembly of those atoms into planets and life and consciousness. A story that continues through you in this moment and that will continue beyond you. When this moment passes, and knowing this, feeling this connection to something larger than yourself, you can rest deeply, securely, peacefully, drifting into sleep as the universe drifts through its expansion. Both movements natural and inevitable and beautiful. And in sleep you will dream or not dream. Will process the day's experiences or simply rest in darkness, and either way is perfect. Either way serves its purpose. And when you wake, the universe will still be there. Still mysterious, still expanding, still bigger than expected, still inviting wonder, and you will be part of it, as you have always been, as you always will be. And this knowledge can accompany you into sleep like a gentle companion. A quiet reassurance that all is well, that the cosmos continues its ancient dance, and that you are held within it, safe and supported, floating through the vast darkness toward rest, toward peace, toward the deep quiet from which you will emerge, refreshed and renewed, carrying within you perhaps some fragment of tonight's journey, some small seed of cosmic understanding that will grow in its own time and in its own way. But for now, only sleep, only rest, only the gentle dissolution of consciousness into the greater darkness, as the universe expands around you and through you, and as you, becoming less and less distinct, fade into dreams, into nothing, into everything, into sleep.